Okay, lesson 1, calculus. Here we go. We are starting about rate of change. And I don't know that we've ever explicitly talked about rate of change in our math classes, but we've talked about rate of change. When we do slope, that's doing rate of change. And so that's the direction we're going here. Can change occur in an instant? And if we look at what's here, as students of life and algebra, you have studied many rates of change for different situations. How fast we drive, how our savings grows over time, the rate that the world population changes, our growth rate every year, unemployment rates, and so much more. In each of these studies, we can express one variable in terms of another, that is, as a function, keeping in mind that y is equivalent to a function, or f of x, where f represents a function and x represents the input. Now we're going to first talk about velocity. You guys haven't had physics, have you? Are any of you in physics right now? So some of you go to physics right after my class? Are you the oddball?
Yeah.
Okay. I was like trying to scan hands real quick, but so you guys are all doing it back to back. Okay. Which there was an advantage when we had C lunch because you had a gap in between. And now you won't. But I will say Mr. Kevin is usually good about, like, if he's trying to schedule a big test and he realizes we have a lot of the same overlap, he usually kind of tries to check and see where we're at to not double you guys up too bad. But okay, so velocity. Consider an object that travels in a straight line. The average velocity over some given time interval can be defined as the ratio of the change in position, so displacement or net change, so how far it travels if it starts at A and goes to B, to the elapsed time period. When we talk about, well, you'll notice the word ratio here, and when we talk about average velocity, we usually say change in distance over change in time. Now, notice I put a little triangle there, right? Actually, I guess I have position. You could say change in distance, or you could say change in position, is what I actually had written in my notes. But that little triangle, are we familiar with the little triangle? I feel like I've used that on occasion, but it just means change. It's the Greek letter delta, and it means change. So change in distance over change in time, or change in d over change in t. So when we talk about average of anything, that's what we're doing here. Change in something in regards to change in the other piece. So in this case, change in distance over change in time. Now, what we're actually going to go with this, because if you notice, concept is instantaneous rate of change. So when we think of velocity, we usually mean instantaneous velocity. Okay? You usually talk, okay, how fast are you going at that moment in time? So that idea, which indicates the speed and direction of some object at a particular moment, which could be faster or slower than the average velocity. Okay? So now the question is, why can't we define instantaneous velocity as a ratio? Okay, so like right here, this is a ratio, right? It's a ratio because it is a fraction, essentially. Yes? Okay, so we have this ratio. This is for average velocity. So the velocity over, so when I talk velocity, I'm basically talking, well, I don't know if I want to say speed. Yes and no. Okay, there's slight differences there, but instantaneous velocity. Why can't instantaneous velocity be defined as this ratio?
Because it's like a certain moment, and then that's it. Not a certain moment? That's more than a certain moment?
Well, so if it's at a certain moment, go ahead.
It's not over a time period, it's at one given point.
Okay, so if it's at a certain moment, what is that time period? If it's at a certain moment, that time is a time period of not even 1, but 0. If, like, if it's from, this moment to this moment, when you if that's the same moment, that has a difference of 0. And what do you know about 0 in a denominator? It's not an option, is it? You can't divide by 0. And so when we talk about why can't we define instantaneous velocity as a ratio, because that time interval would cause division by 0, and we can't divide by 0. So that's what I'm going to write here is the time interval would cause division by 0. Now, if instantaneous velocity is at that one instant, so there's, a time period of 0, so we can't do that because we can't divide by 0. How can we estimate instantaneous velocity? Because that's what we're going to do today, is we're going to look at how can we estimate it. So we can't have exactly a time period of 0. Can we get very close to a time period of 0? And that's what we're going to practice with, is we're going to take a time interval and we're going to shrink it. We're going to shrink it a little bit more, shrink it a little bit more, and look at what the common number is there. Okay, so we're making an estimate. So how can we estimate an instantaneous velocity? And the answer is to make the time interval very small, which we're getting ready to practice. And that bold statement that is next, it's actually also at the top of my page, is important there. Average velocity over a very small time interval is very close to instantaneous velocity. Okay? Oops, what did I hit? So right there, average velocity for a very small time interval is very close to instantaneous velocity. My board is lagging, so I'm looking at my pen like it's running out of ink or something. Don't ask, that's what I think. It's running out of ink. Okay, so average velocity, very close to instantaneous velocity over a very small time interval. Example, if you climb to the top of the Tower of Pisa and drop a coin to the ground, estimate, so notice it's estimate, the instantaneous velocity at t equals 7/10 seconds. Use Galileo's formula, S of t equals 16t squared, to compute the average velocity in feet per second over the time intervals listed below. And then we'll answer the question of what is your estimate for the instantaneous rate of change. Okay, so let's see. They're asking about 7/10 seconds, right? And of course, a formula is provided. Galileo's formula, S of t equals 16t squared. Now, average velocity. How do we find average velocity?
Distance over
Okay.
change in distance.
Change in distance over change in time. Now, in this case, our time intervals are given. So the first one's already done for us. But what we're doing there is we're doing the change in the distance, or the change in the placement, which what tells us the distance or the placement? It's that formula right there. That formula is going to tell me, in this case, it's a drop, right? So how high that point is at each moment. And so we're going to use that formula to find our distance. We're going to subtract them, and then we're going to subtract the amounts. So for instance, to do this one right here, and I think I'm going to write it off to the side because I didn't really write it in my notes, but in order to do that top one right here, you would have done the function evaluated at 0.71 minus the function evaluated at 0.7 divided by change in time, which is 0.71 minus 0.7. Okay, that's what would have been done right there. That's where your 22.56 would come from. Now, I wrote it as S of 0.71 and S of 0.7. Do you understand what I mean there? Okay. It's that equation with those numbers plugged in, right? So essentially what it's doing is it would be doing 16 times 0.71 squared minus 16 times 0.7 squared, right? Are we okay with that? Because that's a concept we have to understand. In calculus, especially as we work towards AP and stuff, you would more likely see them write s of 0.71 minus s of 0.7 than you would see them write the equation out. Okay? So I want you to understand that concept. Now, can we do it for the next one? Okay. Change in distance over change in time. And this is where I said have your calculators out today, right? Now, I figured out a shortcut on my calculator. And again, this is where watching that video last night helped certain things. Let's see. A shortcut in that, are we going to have to use that equation several times? We are, aren't we? Let's see. Okay, what's going on here? I need to be on HDMI.
On that formula where you put the s's like as the function, do those need to be squared as well, or did you predict it?
They represent the.
Oh, they represent it. Okay.
When I have s of 0.71 and s of 0.7.
Yes, those aren't squared because it's
Because it's putting it into the whole function.
Okay.
And like when we get to the next page, we have like a rather long formula on one of these. And the reason I'm showing you this here is because I don't have to type this formula in every single time. Okay. So, grab your calculator, and we're going to use the same equation several times in a row, yes? Now, this equation isn't bad, is it? And so maybe I shouldn't demonstrate on this equation. But what I'm going to do is the equation I'm going to use several times, I'm going to put it into my y1 setting. So 16t squared, in my case it's going to read 16x squared. And note where you put that. Mine's going in y1. Yours is probably going in y1 unless you have something you really don't want to get rid of, but we're on day 1 here. So, yes.
I forgot how to change it back from where as like R1 instead of the Y.
So go to mode, and you want it to be on function mode. Is that what you need to know?
Yeah. Thank you.
Must be the last thing you did on the final exam. Okay, so I put that in Y1. That is function Y1 now. So now, if I go, don't clear. Don't follow that bad example. Oh my goodness. Sorry guys, rusty. Okay, now if I go back to my main calculation screen, if I'm going to use my next figures. So I'm going to go ahead and set up a fraction bar because that's going to be the easiest. And I'm going to do my function. So what was my function? It was y1, right? If you use your alpha button, I know you guys can't see, and then you go over to the F4 menu, which is the trace button. Now, do we all have the calculators that do that? I think we do. Notice I get y1 right there, yes? If I do y1 and parentheses, and what number am I wanting to evaluate at first?
0.705.
So type in 0.705. You see where I'm going with this? Into parentheses. And then we're going to subtract the same equation, right? So alpha F4 is my shortcut there. Y1. And then this time, what value am I putting in parentheses? 0.7. In my denominator, 0.705 minus 0.7. Sorry guys, I'm getting it's hard to see my calculator screen up there, isn't it? I have a glare that, well, that's a little bit better, depending. Okay. Did we get the answer we're supposed to get? Yes. Now, again, this equation was easy, wasn't it? But when we get to an equation, where is it? Oh, it's over in example 3 with the roller coaster. I don't want to have to type that equation in with a whole bunch of different values. Okay. It's at the top of page 3. I don't want to have to type that equation in a bunch of times. I want to type it in once and be done. Now, we need to find the next one, yes? What's changing now? Instead of using the 0.705 and 0.7, now I'm going to be using 0.7001 and 0.7. You can retype the same thing, or I don't know, there might be some advantage of going up. Is there an advantage or not? You could go up and copy it, right? Although then you're going to have to insert characters, but it's doable. Because then I can just change my values. The bottom is easy. 0.70. And then what I can do is I can do an insert 1. I taught you guys how to insert characters last year, didn't I, or no?
Yeah.
It might depend on which class period you're in. Because Miles is giving me this crazy look and Megan is saying yes. So,
I don't know.
okay. So, if I go right here, it's 0.705. Well, when I type a 0, it replaces the 5, yes?
Mhm.
If I type another digit, it's going to replace the parenthesis that I don't want to do. So, I know I mentioned it at least somewhere. Your delete button, right? The DEL button. Above DEL is INS, which stands for insert. So if I do second insert, it will allow me to insert the 1, and it moves over my parenthesis for me. Does that make sense? And so now I don't have to retype the whole thing. 22.4016. This is part of the reason her video was so short. She paused her video and said, do these. She said, pause your video, do this, and come back later, and just filled in the values. So. Or retype the fraction. The fraction isn't that hard to type in, but does everyone figure out something that works for them? What are the shortcuts? I kind of like the copy and paste idea. I just have to insert an extra character. So this time it's 70. Is there 3 zeros there? If your values aren't coming up, you're not hitting something right, yes? And one more. Obviously, I didn't put a lot of work on the screen here. You obviously write whatever work you need in your calculator to remember how we got these answers. Write in your notes, not calculator. I think I said the wrong thing there. Okay, so those are the average velocities at each of those time intervals. Those time intervals are getting very, very small, aren't they? This last time interval, tenths, hundreds, thousands, 10 hundredths, thousands, 100 thousandths, millionths, is what, a millionth of a second difference? A millionth of a second is that last time interval. Are we getting very, very close to instantaneous velocity? Yes, we're getting very, very close. And are you noticing a trend? What are we going to end up at? We keep going. 22.4. So when it asks us, what is your estimate for the instantaneous rate of change at 7/10 seconds, I'm going to say 22.4. Now I need a label. It was change in position, or change in distance, over change in time. What is my position label here? There it is. Feet over change in time, which is second. So 22.4 feet per second at time t equals 0.7 seconds. Okay. Okay, what you need there. Okay. We start off today talking about our first calculus lesson is about velocity. But where we're leading into, our first unit is all about limits. And that's where we're leading into. Not going to really talk about limits today, but the idea is we allowed the time interval to shrink to 0. So we can say that the average velocity converges to the instantaneous velocity, or Instantaneous velocity is the limit, key calculus word there, of the average velocity. Because that's what we were really doing. We were doing the limit. We were doing the limit as t approached 7/10. As t got closer and closer and closer to 7/10, what was that value? So instantaneous velocity is the limit of the average velocity. Now, we're going to look at a little bit of graphical representation here. Average speed is, and her abbreviations, I don't know that I've ever seen the abbreviations quite like this, but I could figure it out. So AROC. Can you figure out AROC? Average rate of change. So when you see her AROC, it's average rate of change. And then, of course, IROC is going to be instantaneous rate of change. So she uses those a lot through these notes, just so you can get the vocabulary there. Average rate of change, her average speed, is defined by the total distance traveled, d, divided by the elapsed time period, t. Okay, so kind of what we already talked about, right? Change in distance divided by change in time. Graphically, the average speed is the slope of the secant line. Now, we have 2 points here. Do you remember what a secant line is by definition? If you want honest, I looked up the definition of secant last period. Not that I don't know in my mind what it is, but yet I was like, what is it? And officially, I'm trying to remember how exactly it read, but it is a secant line is a line that intersects a curve in 2 or more points, as opposed to a tangent line, which is what we'll talk to next. Because a tangent line just meets a curve at 1 point, right? If a line is tangent. So a secant line crosses the curve at 2 or more points, I believe is how it was defined. So here, we're talking about a secant line. We're going to sketch the secant line through A and B. Okay. Me drawing a straight line on the bin Q. Not horrible. So there is my secant line. And basically, we want to find the average speed is the slope of the secant line. So if we find the slope of the secant line, so that's m with a little secant there, or here, I'll make it. If we find the slope of the secant line, we are finding the average speed. What are these points that A and B are at? So A is at 1, 3, and B is at the point 4, 4. Okay, so the slope. Well, yes.
So the purple line is the secant line?
Yes. Because it goes through the curve. So the curve being this black thing, it goes through the curve it crosses through the curve in 2 or more points.
Okay.
And it crosses through at point, well, I call those points A and B. I guess they're not points A and B, but the 2 points that are there.
Okay.
Are we okay with that? Okay. So I sketched it. How do I estimate average velocity here? Well, average velocity, average speed. We're going to do rate of change, yes? So average rate of change is going to be my slope of the secant line. Slope. How do I do slope? Yeah, y1 minus y2 over x1 minus x2, change in y over change in x. So in this case, I'm going to do 4 minus 3 over 4 minus 1, which is 1/3. Okay, so that represents our average rate of change. That represents the average speed. Again, it's looking at slope, but it's also exactly what we were doing on the previous page. Okay. Now, instantaneous. So IROC is the speed at a specific instance in time where t is equal to t naught is the limit of the average rates of change. I totally butchered in reading that. Yikes. Okay. Instantaneous speed, limit of the average rates of change. That's what I need to be saying. Okay. Graphically, okay, so when we look graphically, instantaneous speed is the slope of the tangent line. Okay. So tangent line, do you remember what I mean by a tangent line? A tangent line is going to go through that point, but it's only going to touch the curve at that point. It's not going to cross through the curve, right? I mean, I always feel like we know tangent lines better than we do secant lines. I don't know why, but I do. So our tangent line is going to go right through there. And now, getting us all to draw the same tangent line, well, yeah. I kind of know where I want it to end up, but not the best. But that's the idea of the tangent line, right? And if you're trying to get it in the same area as me, I was trying to get it to go through that point, make sure I went through that point right there, because I know ultimately that that's the area we're going to be in. Because those are the 2 points I'm going to use here. The point already given, and then, yeah. So we have a point at 5, 6, and a point at, what, 2, 4? And this time, though, instead of talking about the slope of the secant line, we're going to be talking about the slope of the tangent line. So, I knew where I was going. Sketch the tangent line through point C. Can you estimate the instantaneous velocity at x equals c? Well, we can estimate. We can do slope here. So when we talk about our instantaneous rate of change, we're doing the slope of the tangent line. I wrote in the ordered pairs. I guess you don't really need the ordered pairs, though. How else can I do slope? Instead of just looking at the graph, or instead of using ordered pairs, we can look at the graph and count. Yeah. Phrasing I'm looking for here is, yep. That's buried in those heads somewhere, right? Rise over run's not too deep. You know that one. So if we rise over run, go up 2 over 3. And again, it's an estimate, right? It's an estimate. That tangent line is not actually precise, but it's an estimate. Yes.
Why did you go to 5, 6? Like, how did you go to that point?
It's not that I knew where I wanted to land is what it came out to, but what I'm trying to do is draw the line so that my line only touches this curve at one point. And that one point being this point, what they call point C, or 2, 4. So I want to make it so that it's not hitting the curve, like hitting this curve for an extended period of time. That it's just kind of a touch and go, if that makes sense. So as I draw my purple line, the idea is it's going to touch at that point, and then it's going to not be touching anymore. I don't know if that makes sense. It's kind of hard to, honestly, I just knew that I needed to land at 5, 6 to be in the ballpark. This is an estimate, yes? Could yours have been slightly different if we weren't doing this together as a class and still be an appropriate estimate? And the answer is yes. Okay. So it's not that you had to land at that point. It just, that was kind of the ballpark of where I was looking to land. Okay. Let's see. I'm trying to remember what example 2 was. So, have you ever taken a spin class at the gym? Then you know that after class is over, your rapid heart rate decreases as time passes. Let's just go with any exercise, right? Get your heart rate up, it decreases as time passes. Let h of t represent your heart rate. Write an expression for the rate of change of your heart rate over the period from t equals 0 seconds to t equals 90 seconds after you have stopped exercising. So we don't have all the information to find the rate of change of your heart, but we're going to write an expression. Good calculus concept here. How do I write this an expression?
Something over something.
Okay. There's the start. Something over something. I agree.
90 minus 0 is at the bottom.
Okay. I can agree there. 90 minus 0 is at the bottom because on the bottom is going to be our change in time, if you will. Yes? And our change in time is 90 seconds to 0 seconds.
You just put variables at the top.
Not just any variables. Something specific to this problem here. I guess it's more than just variables here, but kind of think of how we were expressing things on the previous page.
Is it the h90 minus h of 0?
Mm-hmm. Yeah, because it's the rate of change, yes? Just like we were finding rate of change on the front page. On the bottom, it was the change in time. On top, it's going to be the change of, what are we talking about? The heart rate, yes? So it's going to be the heart rate at time 90 minus the heart rate at time 0. And let's see. I did not clean it up past this. The only cleanup you can really do is 90 minus 0 is 90. However, it asked us to write an expression, yes? Do we have an expression? Yeah. If we talk about a label, what kind of label do we have? Change in heart rate. What's our label for the change in the heart rate? Beats. Per change in time. What time are we talking about? Seconds on this one. So beats per second.
Are you a spin class guy?
Yeah.
Okay. Ready? The next page? Example 3. A hypercoaster is a special circuit roller coaster with a height measuring greater than 200 feet. If a new hypercoaster is under design to have its largest drop on the circuit modeled by the equation below, where d of t is measured in feet and time t is measured in seconds. So how many times do you want to plug this equation into your calculator? I want to plug it in once and be done, right? So that technique I showed you a little bit ago where we can put it in y1 or y2 or y3 or whatever, we can do that, and then for the duration of the problem, you can do y1 at blank time. That's why I showed you that trick, okay? I made sure to figure out that trick before class today because I knew I could use like y1 and y2. I didn't realize I could put a value into them. So that was new to me. Okay, so A asks us to find the average speed or velocity of the hypercoaster from 2 seconds to 8 seconds. Average speed. What are they asking for here? Average rate of change. So if we're trying to find the average rate of change from 2 seconds to 8 seconds, what are we going to set up? D of 8 D of 2. All over 8 minus 2. Change in distance over change in time. So if you haven't already typed that equation in, by all means, type it in. Type it in. And you can make it Y1. You can make it Y2. You can make it Y whatever floats your boat there. Okay, so go back to your regular screen if you haven't already. I really prefer a fraction bar in this setting. Okay, so whether you're doing that or not, I definitely do. So I'm going to do y1 evaluated at 8 minus y1 evaluated at 2. You do have to put those parentheses afterwards because I tried it this morning without parentheses and it wasn't working. At least the particular example I did. Oh my gosh, you guys can't see my calculator at all. What is up with?
I might be able to turn like the brightness down or something.
I wonder if it's that blue paper causing the problem, because sometimes the color paper, that helps some. Okay, did you guys match my answer? If you did not match my answer, I'd go back and start checking, did you type everything in the calculator correctly? And think about a label. What kind of label would I say? 63.47. Right, because it's change in distance over change in time. What is my distance measured in? Feet. What is my time measured in? Seconds. So feet per second. Okay. B. What's the average speed of the hypercoaster from 4 seconds to 6 seconds? Same idea. Average rate of change. This time I'm doing D of evaluate at 6 minus D evaluated at 4 over 6 minus 4.
Sorry.
Yes.
For the first one, I got like 32,000 something. And I checked all the numbers and got all right.
That's a fast roller coaster.
Oh, I didn't put minus, I put I
That's exactly what I was getting ready to tell you. Forgot a subtraction sign. When you multiply those values on top rather than subtracting, it's going to make a slight difference.
That sounds like a fun ride. I wonder.
Sounds like a dangerous ride to me.
Oh.
Did it work that time, Jacob?
missed it.
Okay. Sorry, I'm asking too quickly here.
Put it in wrong. Alright.
Okay, good. As I said, if you're not getting it, it's probably just he didn't type a number wrong. He left out a subtraction sign. I mean, you know, something silly. Okay, so if you change those numbers to 6 and 4, which I honestly would have just copied what I just already typed in, because that'd be really easy to change my 8s and 2s to 6s and 4s, wouldn't it? Or retype the whole fraction. What do we gain this time? 48.51, I think. And that is feet per second. Now, I don't know if you're watching, you know, but that was the average speed from 2 seconds to 8 seconds. Now we're doing the average speed from 4 seconds to 6 seconds. We're shrinking our time period here. Okay? Now, a little bit of notation here I had written in my notes. Your average rate of change here on, and a way to write this interval would be 4 less than or equal to t less than or equal to 6. So the, you know, if we're getting some official notation here, the average rate of change, that's saying between 4 and 6 seconds, is, and that is the 48.51 feet per second we found. Okay. When it comes, I know we haven't, I'll throw in bits of pieces of information about the AP exam as we approach, but the AP, you have part of it's multiple choice. You have part of it is free response. Free response, here's the question, you're answering, but, appropriate language, math lingo, words, labels, that type of stuff is all stuff they'll point on. Okay, so C. Estimate the instantaneous velocity of the hypercoaster at exactly 5 seconds. So, what's set up for us there? A chart, yes? So on the first time interval, it's kind of really a big interval in this case for instantaneous, but 5 to 5.1. So of course you realize that you're doing the function d evaluated at 5.1. It's the function d evaluated at 5 over 5.1 minus 5. Got 3 different ones to fill in there. Or at this point, do we have the calculators filled in? Would it be easier for me to just tell you the values?
Yes.
I'm just realizing because that's, that takes up time that as long as you've got the calculators figured out, I can go ahead and tell you first one I have is 47.3997. Of course, these are all velocities, so feet per second. Next one I have is 46.7142. And last one, 46.6474 feet per second. I don't know that we know the exact value it's getting closer and closer to, but we're getting a ballpark, aren't we? Okay, so part D asks us, explain the meaning of the instantaneous speed or velocity in the context of the question at 5 seconds. So what is this representing?
Where it's at 5 seconds. Like height. Is it height?
Well, and if you look at what the equation represents, it's not just the height, but the drop, is it? Yeah. So it's measuring the drop is what it's, if you go back and look at what the equation is defined, it's defined to be measuring the drop in feet per second. So when we talk about this, our rate of change here is the drop of the hypercoaster at 5 seconds. And so the rate of change of the hypercoaster at 5 seconds is about, and we don't have it exactly, but we can use our, we can keep going farther. We can use that one that we have. And we have it as the 46.647 would be your minimum expectation. So our rule of thumb this year, AP requires 3 decimal places all the time. Rule of thumb, 3 minimum. Okay. Now, will I often maybe go more in a situation like this to, give us a little bit more? Yes. But when you give a final answer, you want to give 3 minimum decimal places. Unless there's something specific, I forgot my label here, feet per second, always go 3. I don't know that I can do this, guys. We're so close, but yet not there. Okay. Airport. And some of this is repetitive, but some of it is stuff we need to talk about. So airport departures. The traffic pattern of departing flights at Orlando International Airport on a fall afternoon can be modeled by the function v, defined by v of t as 92 minus 15 sine of t over 3, where v of t is measured in what? Vehicles. Just saying, because we've talked a lot about velocity, yes? Maybe it's just me, but when I see this v of t, my brain goes to velocity, because that's what we've talked about. But this v of t is vehicles. Now, find v of t for 18. What's that mean you're doing? Plugging in 18, yes? So you're plugging in 18 to the 92 minus sine of 18 over 3. Do we use this v equation several more times? Yes, we do. So might you want to make this v equation into your y1? You might. So 92 minus, oh, I forgot something, didn't I? Did anyone catch that? I didn't forget it. It's right there the whole time. No? 92 minus 15 sine of x divided by 3.
We don't put that 18 in there.
Not when you're just putting it into y1. Okay. Because I just put it into my y1 so that I can now, I mean, that, if you're just going straight into the value, that's fine, but we're going to have to use y1 multiple times later, right? So if I do y1 evaluate at what, 18? Is your answer matching my answer? Are we in the right mode? What mode matters here? You might all be in the right mode.
We need radians.
We need radians. Are we not in radians?
I'm not in radians.
Okay. Which, by the way, that's going to be a big thing this year. You need to be in radians and calculus. You'll have to be in degrees for physics. It's a challenge going back and forth.
Whoa.
Yeah. Mr. Kevin will usually need degrees. I will usually need radians. We don't usually do a whole lot with degrees in calculus. Not to say it won't happen, but. Okay. Does your answer match my answer? 96 point. If we go 3 decimal places, that is 191. And what is that? That was V, where V is measured in vehicles and T is measured in minutes, right? So that is 96.191 vehicles per minute. Or in other words, since I'm not sure we really want to talk about 96.191 vehicles, it is about 96 vehicles.
So is this instantaneous thing, or is this is an average, right?
This is more, it's not really either of those because it's just using the equation there. Now, it asks us to make a sketch of the graph of time versus number of vehicles. That's using your calculator at that point. This is not something that we would graph by hand. You definitely do have to change the window in this. And actually, I already have the equation typed into my graph, don't I? If I, since we're about out of time, window settings. There it is. I was like, I know it was given here somewhere. Your t values, so in this case, my x-axis needs to go from 0 to 30 because they provided that, right? So you want your x-min and x-max to be 0 and 30 respectively. Now, you can go ahead and graph, but you're not going to find anything under 10. You want some help to zero it in a little quicker. 70 to 110 are some numbers for your y-min and y-max. Did I spell vehicles wrong there?
Yeah.
Okay. So Megan at least noticed my misspelling there.
I know, I just didn't want to say anything.
Hey, I got it right up above, so
That class, it didn't matter.
not a huge thing, but okay. Oh, I didn't actually graph mine, did I? Of course, you have to be in radians. Kind of looks like a sine curve, right? Which it is. I mean, it is a sine curve, so it's just a variation of a sine curve. But if we fill in, I'm not going to get very specific here. 10, 20, and 30. And that is for the time axis, measured in minutes. Along the left, I did 70 to 110, didn't I? So, well, I have some other values in here, and that it goes about as low as 77. It's on the y-axis at 92. And again, these are numbers I've already figured out. Goes down to about 107. That's not exact, but it gives us a little bit of a sketch to look at. And if done correctly, my 18, yeah, it's not done exactly correctly because I didn't sketch it correctly, but the point, when we plugged in 18, we came out at 96.191. That point should be right there. And it should be better on my actual graph. Okay, bell's going to ring on me. We only have 3 parts left to do. So here's what I'm going to ask. The homework is on the next page, front and back, yes? Go ahead and work your way through it. See what you can do with it, okay? Obviously, I have to finish a few examples. I'm trying to remember if those examples, the parts I have to finish matter to the homework or not. Does that make sense? Because what we'll probably do is we'll finish up 1-1 and deal with stuff there. And I may try and go on to lesson 2 as well tomorrow. It's just going to be kind of a see, okay? We'll kind of see how it goes. I got to figure out my routine for this. Sorry. It's going to take me a bit this year. So do what you can with that, and I will see you guys tomorrow.